Google Meet, we should use Zoom. And the reason I'm thinking of using Zoom is because I really do want people to, I want to be able to see you. I don't care if you're not paying attention. I don't care if you've left the room. What I want to know is, are you not paying attention? Have you left the room? Are you just on your phone? Are you drinking a coffee? Are you playing with your dog? And I'm not going to yell at you if you're playing with your dog or you left the room, but I'm also not going to ask you questions either if you've left the room. Or if it looks like nobody's paying it, that's good for me to know if nobody's paying attention. When all I see is nothing, just your little symbol there, I don't know what you're doing. So I was kind of wondering why people don't want to turn on their cameras. And some ideas I came up with are, one, they want to do other things and they don't want me to know. Two, they don't want people to see their rooms. Three, they just don't like being on camera. I think those are all the reasons I can think of. So the good thing about Zoom is you can make a background. So if you don't want somebody to see your messy room, then you can have some different background so nobody has to see anything in your house. The bad thing about Zoom I've heard is that I've heard people have a harder time connecting, that it uses more bandwidth. Megan, did you want to say something? What's that? Oh, on a Chromebook you can't? Oh, even with Zoom. Oh, that's a good point. I didn't know that. It would be okay if people use phones. Now, not everybody would necessarily have a phone, though. So, at any rate, if you don't want to turn your camera on, I'd like people to explain to me why you don't. But you don't have to here. You could just email me or let me know sometime, because it really is good to see what's going on your end. Like in the classroom, like Reagan right now, he's playing with his wristband, and I know that's constant feedback I'm getting. I'm not saying you keep playing with your wristband, but I know he's playing with his wristband. And so Harriet's looking at me. I know she's listening. So if I were going to continue the conversation, I might talk to Harriet because Reagan's not paying attention anyway. Were you? Okay, all right. But anyway, we wouldn't even be having this conversation if there were just a black rectangle there with, what is yours? Some kind of cat thing?
Totoro.
Totoro, yeah. Totoro looks kind of cat-like. Hello, Mandy. All right. So the blobs and the lava lamp. Let me go back to this. RJ, can you hear me?
Yeah.
All right. Good. Let's see. I've got to watch out for this thing up at the top. It looks like it covers up some of my tabs. I wonder if there's a way I can move this. Let's see. Huh. I just made it bigger. Yeah, maybe if I pull it the other way. Seems like I ought to be able to put it somewhere else. Oh well. So here's the lava lamp. The blobs are going up and down. And I'm going to ask somebody, just to pick a kind of a random person here. Oh, Megan. Why did that one that it's just going up? You can either tell me why it's going. Oh, what? Was that a problem? Okay, so you can either tell me why this just started to go. I don't know if this thing's as good as he says it is. Maybe it was because I messed with reconnect. By the way, this is Carl Sagan, and Carl Sagan made a movie or video series called Cosmos that was remade by Neil deGrasse Tyson, and we're going to be watching some of that today. So Megan, one of those blobs in just a second is going to start to sink, and right down here at the bottom, pretty soon this is going to be another blob that's going to start to rise. Tell me why either the one that's rising rises or the one that's sinking sinks. Any ideas at all? I'll give you a hint. It has to do with it has to do with multiples of these, but there's a key. Mass, volume, density, or weight? Which one of those is most important when we're talking about something rising or sinking? What? Density. So the ones that are going down, like the one that's going up, is it more dense than the liquid around it or less dense? More dense? Less dense. So the lower the density of something, the more likely it is to rise, and the higher the density of something, the more likely it is to sink. So the Earth right now, well, the Earth always, since it was formed, remember, has all these layers, and it's got the crust on the outside, then the mantle, then the outer core, then the inner core. And where's all the densest stuff? Anybody? Just inner core. And it sank. So we being upright like we are, if the Earth were molten and I dropped a piece of iron, it would sink right through all this rock, which would, if it were liquid, and it would go all the way down to the inner core. If I dropped a piece of rock that was the same density as the stuff we're standing on, it would just kind of stay up here. It wouldn't sink down where the deep stuff is. So that's what's happening here. Everything that's rising is less dense than this clear liquid. Everything that's sinking is more dense than the clear liquid. Now, the next question is why? Why did that rising blob, why did its density change? It was less dense as it went up, but it's going to sit there, and after a while it's going to be more dense and it'll sink back down. Raise your hand if you want to answer this one. Jace. What? So it gets hotter, and hotter things become less dense, and colder things become more dense. And there's an exception to this, but in general, if you heat something up, it's less dense. If you cool it down, it's more dense. Elijah, can you explain why? Why are hotter things less dense?
The molecules that spread further apart.
Right, so this is a bad example, but this tape here has a bunch of molecules inside, and right now they're solid, but they're still vibrating around in place. They're just kind of doing this. And if I heat them up, they do that harder and harder and harder, and they start to spread out from one another. In a gas, if you just picture a gas or this blob right here where things are more flexible, as you heat those up and the molecules start to bounce around, they spread out again. And when they push away from one another, are they getting more crowded or less crowded? Less crowded. So when things heat up, the molecules move faster. When they move faster, they push away from one another, and that spreads them out, which makes them less crowded and less dense, so they float. So this same thing happens inside the Earth. We've got some spots in the Earth that are particularly hot, like this, and that heats up the magma or the stuff that's in the mantle around those. And when that heats up enough, it expands enough that it starts to rise up, and that creates these upward convection currents, they're called. And then that material that gets to the top cools off, and when it cools off enough, the particles come back together, and then they get crowded and dense enough to sink again. Except inside the Earth, it's not like things go up here and come down here. They go up here, and they move over here, and then they come down, and then they cycle back to here, and they heat up. And they go up again, and they cool down, so you get all these circulating cells. All right. Oh, I've got some more people at home. So now I'm going to go to the Quizlet. I'm going to quiz people, but oops, I have to text my daughter. She took my Chromebook to school, not hers. So I have to give her my password. All right. So people at home, get ready. I'm going to be asking you, oh, turn on your cameras. I was just having a conversation here about why you have your camera off. So all I can see is 3 blacknesses. I don't know if you're in the other room. I don't know what you're doing. If you're just sitting there not paying attention, that's fine. I need to know that. So turn your camera on so I can see that you're not paying attention. Just unless there's some really good reason, bad connection, I'll have to trust you on that. Email me if that's the case. Okay, so Quizlet. And thank you, RJ. Thank you, Tyler. Solely. Flashcards. I'm going to, how do I shuffle? Maybe it's too late to shuffle. Let me go back. Oh, shuffle right here. All right. So, Anna, where's the coolest part of the Earth, and why is it the coolest?
The outside, so the crust, because of the air and
You were on the right track. It's the crust. It's the outer part, and the outer part is coolest because of outer space. Space is really cold, and the atmosphere is actually like a blanket. Here, I need to. Yeah, you didn't really finish the second part. You didn't finish the coolest part, but you were on the right track to get it. Let me do this so I can go back and forth between these, and I can still gesture and stuff. So this is the Earth. Space out here is really cold. That cools off the outside of the Earth. But since we have an atmosphere, that actually prevents the Earth from cooling off too fast. If we were like Mars, where there's not much atmosphere, the Earth would cool off a lot faster. Or Mercury even. There are some planets that don't have atmospheres, and space cools them off more. So the answer, surface is coolest because it's closer to outer space, which is cold. Oh, and then another one. The pressure. The pressure is the weakest at the surface. Next question. A current formed by differences in densities. Mandy, what would that be? What's the name of a current that's formed by differences in densities of hotter and cooler parts of a liquid? Don't know? Let me pick somebody else. Reagan. What's the name of that current? Don't know? You're supposed to... Quinn. Yes, it starts with a C. Good job. Convection, yeah. So convection current. There are three kinds of ways heat gets transferred that we'll talk about at some point probably. Convection, conduction, radiation. We've talked about radiation. Conduction is just when you touch something and it's hot. Like this phone were glowing hot. It would make my hand hot if I just held it here, but if I touched it, conduction's really fast. Fast way to transfer energy. All right, this type of plate boundary forms over cooler parts of the mantle. Elijah forms over cooler parts of the mantle. This is a hard one. This is putting several things together. Let me see if this jogs your memory. We have two plates like this, and then we have a cool part of the mantle. Is this going to rise or sink? Sink? And then right in here, are these two currents going to go apart or come together? Come together. And does anybody want to help out? What kind of plate boundary is this where two things come together? There are three types of plate boundaries. There's transform, convergent, divergent. What do you think, Megan? Convergent. Convergent. So, and the reason this is convergent is the cool stuff sinks. That creates this current that pulls things together at the top. And when two plates come together, they converge. So that's a convergent plate boundary. That was a tough one. That's putting together a lot of stuff. Okay, explain why the Earth's hottest layer is solid, even though it's hot enough to be a liquid. So usually, when you heat things up a lot, they become liquid. But this is hotter than it needs to be a liquid, but it's still solid. Harriet. Why? And I'll tell you which layer it is. It's the inner core. So why is the inner core a solid, even though it's hot enough to be a liquid?
I don't remember. I remember reading this question, but I don't remember.
That's okay. That's fun. This is not the real quiz. This is just practice. So remember to study more because we'll have the real quiz tomorrow. Anna, do you want to answer?
I think it's because it's too uncomfortable.
Right. There's so much pressure. So as I told you yesterday, this is kind kind of sounds backward. It's like I say one thing and then I say the opposite. So if you imagine the Earth compressing together, that heats it up. And the part where it gets heated up the most is the center. And when you heat something up, usually that liquefies it, that melts it. But at the center, there's so much pressure that those particles can't even move. And the state of matter when the particles can't even move, like this pen, particles are still, it's a solid. So you can keep something a solid if you squeeze it together tightly enough. But if you took some of that stuff from the inner core and you brought it to the surface and you let go, it would immediately turn to a liquid, and it might even boil. It probably would boil. All right. We're getting the hard ones out of the way. That means there must be some easy ones. Okay, so here's an easy one. A place where two pieces of the Earth's crust move away from one another. Skylar. No? It's one of the, I'll give you, you've got 1 in 3 chance here. Is it a convergent plate boundary, a divergent plate boundary, or a transform plate boundary? Converge, diverge, or transform? Which one sounds like moving away? Divergent, yeah. So this is a divergent plate boundary where the Earth's dividing.
A place where two pieces of the Earth's crust move
Oops,
away
I clicked on the
from one
words
another.
instead of that. The name for the place where two pieces of Earth's crust meet. So this is supposed to be a simple one. Solly. Ah, she ran away. All right. So Anna. Where any place where two pieces of crust meet. And I'll give you a hint on this. This one's kind of too easy. One kind is a transform, one kind is a convergent, and one kind's a divergent. But all of those are where the plate meets. It's such a, you'll feel like, oh, that was so obvious. Yes. The plates are the pieces of the crust. Here, I'll pick somebody else. RJ. RJ, do you know?
No.
No? Okay. Let's see.
Laura.
Laura. Okay. Does anybody know? She knows. All right, I'm going to click on it and reveal the answer. It's a plate boundary. So there are 3 kinds of plate boundaries. There's a convergent plate boundary, there's a divergent plate boundary, and then there's a transform plate boundary. And that one was so easy it was hard. What's the inner core made of?
Jace.
Jace, what's in the inner core? I would say no. Magma is usually rock, and this isn't rock in the inner core. I mean, there might be some of what's in the inner core in magma, but any ideas? Megan. Solid iron and nickel. And it's solid because there's so much pressure. It's hot enough to be a liquid. Solid iron and nickel. An individual piece of Earth's crust. Ooh, I'm afraid this one's so easy that it's hard too. Aiden. No Aiden. Cassidy.
I don't know.
A piece of so if you imagine the Earth, people always talk about this. Imagine the Earth is an egg, and it's got the shell on the outside, and you crack the shell. There are all these cracks all over, and one little piece of the eggshell. We've talked about where the pieces come together. There are 3 kinds of boundaries between these things. Any ideas? Let me see if I can. Alyssa. Oh, no, Alyssa. Tommy. Ah. Megan. Do you know? No? Anna? No? Does anybody know? Jace. Tectonic plate. Or you could just say plate. So, again, one that was so easy it was hard. What's the mantle made of? Quinn. Rock. Now, what if you were to describe the rock? Like there's rock in the crust, there's rock in the mantle. How is it different? Okay, let's see.
Tyler.
Tyler? How is the rock in the crust on the outside of the Earth different from the crust in the rock in the mantle?
I don't know.
Don't know? Does anybody know? You could, Anna? The temperature is different. This rock is a lot colder, and the rock down below is a lot hotter. And of the two, which rock can actually flow like a fluid? The rock in the crust or in the mantle? The mantle. So the mantle is made of hot flowing rock. So we're on the plates. These plates are like rafts. The rafts float on the river, and the mantle's the river. So the river moves down here. It's got all these currents in it that do this kind of thing, and they push the plates, and the plates ride on them. So it's got to be hot and flowing. A place where two pieces of Earth's crust move toward one another. So we're back to plate boundaries. This is asking you about this kind of plate boundary where you go toward one another. Let's see.
Solly.
Solly's gone. Aiden's gone. Quinn. Do you want three choices?
Yeah.
They're convergent, divergent, and transform. Which one means move toward, like, together? Convergent, divergent, or transform? Divergent is to divide. Take another guess. Take another guess. It's convergent. So converge means to come together. When things converge, they come together. And diverge means they move apart. And it's okay if you don't know these. We're just studying right now together. Ooh, draw a diagram of some plates and the mantle below them. I'm not going to put you on the spot to do that, but maybe I'll do it myself. I started doing it here, and I'm going to erase this and do it again. And I'm supposed to draw a diagram showing some plates and the mantle below them, and use arrows to show convection currents and hotter and cooler places. So here goes. Here's some plates. Plates are just pieces of crust, and I can make as many of these as I want. And the plate boundaries, they're right here where the two plates come together. And whether or not these plates move apart or together, I could decide in different orders. I'm going to do it this way. I'm going to say this is cooler material in the mantle, and this is hotter. So the mantle's down here. So this tells me this is going to rise, and this is going to sink. And if you saw me blowing the pepper around in the dish yesterday, when this sinks and it gets to the bottom, it's going to split up like this. And when this rises and gets to the top, it's going to split up like that. And as this goes up, it's going to suck something in there. As this goes down, it's going to pull something in there. So these are the convection currents. And these convection currents, they're the river at the top, and the river makes the plates move. The plates are like the rafts on the river. So here, the plates are going apart. This is divergent. And here the plates are coming together. This is convergent. And I think I got it. That's what I would expect you to do. That's not really that hard. Let's see, here's a picture. Oh, I meant to change it up. I drew exactly the same picture. Where are the most dense and least dense layers of the Earth?
Tyler.
Tyler, tell me where the most dense layer of the Earth is.
I don't know.
Oh, come on, Tyler. Guess? Can you guess? Most dense. Do dense things rise or do dense things sink?
The center?
Yes, the center. Okay. So, all right, Tyler, I'm putting you on the spot again. If the most dense is at the center, where's the least dense? You started to talk. RJ, are you going to answer? Anybody here? Just blurt it out. Where's the least dense? The crust, the surface. So most dense is at the center, the least dense is the surface. A place where two pieces of crust meet and slide across one another like two hands rubbing together. All right, Elijah wants this one. What is it, Elijah? Transform boundary.
A place where two pieces
Oh.
of the Earth's crust meet and slide across one
Transform
another.
boundary. Got to watch out. What's the Earth's crust made of?
Harriet.
Harriet. So Quinn had what's the mantle made of? It's pretty similar, but a little different. What's the name of this layer that we're actually touching and made of? It's the crust. So this is all the crust around us. I'm helping you out. Is it a solid, a liquid, or a gas? Solid. Now the atmosphere is a gas, but the crust is solid. And if you were to dig down just a few feet, you would get to what it's made of. What's it made of? Here are the things that are in the earth. There's nickel, there's iron, and there's rock. Of those three, rock. So it's solid rock. That's what the earth's crust is made of. And then if you go down, it gets hotter, and it's not exactly solid anymore because it starts to flow. So three sources of the, so I want one source of the heat inside the earth.
Mandy.
Mandy, what's one thing that makes the earth hot inside? Say that again. So you're doing this with your hands. Do you mean compression? Yeah, so compression, that's one of the sources of the heat.
Jace.
Jace, what's another one? Elijah? Radioactive material in the earth, and does anybody know the third one? Megan? Heat from past collisions, yeah. So compression, when the earth was forming, it squeezed together and it's still hot from that. Radioactive rocks, heat from past collisions. What's the outer core made of?
Solly.
Solly, no.
Alyssa.
Alyssa, no.
Tommy.
Tommy, no.
Elijah.
Elijah, well, you just answered. I'm
Reagan.
picking. Reagan. The outer core? Out. All right. I think you could probably guess it. You ought to be able to guess this one.
Laura.
Laura. So there are really two things layers are made out of. They're either made of rock or they're made out of something else. It's not rock. What's the other kind of thing that you could find in one of these layers? What? Don't know. Anna. Iron and nickel. And Elijah, is it solid or liquid? Liquid iron and nickel. So the inner core is solid, the outer core is liquid because there's not so much pressure there that it keeps the particles from moving. 4 major layers of the earth from outside to inside. List all the layers.
Mandy.
Mandy, what's the outermost layer of the earth? And then I'll pick somebody else. What? Crust.
Quinn.
Quinn, what's the next one going in? Mantle, very good.
Quinn.
Quinn, what's the next one? Outer core. And Cassidy, what's the last one? Inner core, very good. We must be getting, we're at 17 out of 20. 3 more questions. Why are hotter materials usually less dense than cooler materials? This is a tough one. Anybody want to volunteer? Why are hot things less dense than cool things? Elijah?
Because their molecules are faster and spreading through the planet.
Right. There are particles in them, whether they're molecules or individual atoms, they move faster. And when they move faster, they push apart, which makes them less crowded and less dense. Hot molecules and hot materials move faster, so they spread out and become less crowded. Why does hotter material rise and why does cooler material sink? This is from the warm-up. Anna, why does hot stuff rise? Why does cool stuff sink? Just a really basic answer. So which one's more dense? Cold stuff's more dense. Hotter material's less dense, colder stuff's more dense. And this is the last question. This type of plate boundary forms over hotter parts of the mantle. This is a tough one.
Reagan.
Reagan. What?
I don't know.
Let me do this. I'll draw a picture over here. Here are the plate. Here are the plates. This is the plate boundary. This is the hot part of the mantle. Reagan, what's this going to do? Is this going to rise or sink? It's going to rise. And when it gets to right here, these 2 places where my finger are those currents going to go apart, or are they going to go together?
Pretty sure.
Apart, yes. So which way is this plate going to get pushed? Right or left?
Right.
And this plate?
Left.
And now if you look at what the plates are doing, is this convergent, divergent, or transform? Divergent. Very good. So you knew everything you needed to know to get that one right. It's just I don't really want you to memorize the answer to this question. I want you to be able to think about it in your head and think, okay, hot parts, they're going to rise up, and that's going to make a current that goes up and splits apart, and that's going to push the plates apart, which means a divergent boundary. And if this would ask you about cooler parts, you would say, cool stuff's going to sink, and if it sinks, that's going to create currents that are like this. So at the top, the plates are going to get pulled together. That's it. So people at home, you've got a quiz on Monday over this stuff. And people here have a quiz tomorrow over this stuff. And we're going to watch Cosmos for the rest of class, which is, we watched it, the blue people already watched some of this. It's just, it was really nice because you've already learned all this stuff, and I think you'll find it more interesting than if we watched it earlier on. So, see ya. Thank you, too, for showing up and